Hello dear students, welcome back to NEET WORLD. So in this particular session we will be discussing equilibrium, and particularly here we will be covering EAPCET questions related to this particular topic also, equilibrium. Okay, so now today we will be starting equilibrium. Till now we have completed 5 chapters, okay, and previous year questions related to those chapters are also finished. I hope you have watched those sessions. Okay, if you haven't watched, once after finishing this you can watch them. Those videos are highly helpful for your preparation. Okay, right. So now what exactly equilibrium, tell me, do you have any idea on this? See, chemical reactions, there are some chemical reactions. See, first of all, equilibrium will be possible, equilibrium will be exist or possible only in reversible reactions. It means first of all you need to know the basic classification of reactions. How can we classify reactions? Yes, reactions are of 2 types. One is reversible, other one is irreversible. Okay, types of reactions are 2, reversible and irreversible. Okay, and our equilibrium, whatever we are going to discuss now, that will be possible only in reversible reaction, not in irreversible reaction. So when we can say a reaction is reversible or irreversible, it's very simple. See, for example, conversion of some reactant A to final product B is there. Okay, if this conversion is taking place 100% forward, then I can say it is a irreversible reaction. See, reaction which proceeds in one direction, in forward direction only. Okay, it means complete reactants are almost converted into products here. Okay, complete conversion of reactant to product takes place when it comes to irreversible reaction. Okay, and then next, it is when it comes to a reversible reaction, here you can see reactions proceeds in forward as well as backward direction. Let us say I am starting the reaction with this reactant A. Okay, at time t0 what we have, at the initial case what we have, only reactant we have right now. So after some time t minutes, this sum of this A compound, this reactant A is converted into B. Okay, right. After forming this B, that B molecules, whatever it is formed, they themselves combine or they will decompose and they will return back to its original A. It means forward reaction is taking and backward also taking. So this kind of scenario will be observed in reversible reaction. Hope this is clear. Now see, reactants are never completely converted into product. It means 100% completion of reaction never takes place here. Okay, so attain the equilibrium state and never go to the completion. Yes, so once it will attain the equilibrium and it will never goes to the completion. Okay, hope this is clear. Right, let us move forward. Now what I am saying, equilibrium is possible only in reversible reactions. Okay, and what exactly equilibrium means? First of all, understand what is equilibrium, then next we will see types of equilibrium. See, for example, reactant A plus B combining to form some products like C plus D. Okay, right. So the rate of forward reaction, it means combination of these two will be taking place to form this forward products now. So it means rate of forward reaction will be equals to rate of backward reaction. So at this particular condition we can say reaction is at equilibrium. So at equilibrium what happens, rate of forward reaction and rate of backward reactions are equal. I am not saying concentration of reactants and concentration of products are equal. I am saying what, rate of forward reaction and rate of backward reaction are equal. Hope this statement is clear, right? Now see, so this equilibrium is of 2 types. One is physical equilibrium and another one is chemical equilibrium. Okay, what is mean by physical equilibrium? Here no chemical change, only physical change is attained. See, at boiling point if we see, for example, water boiling point if we observe, see, at this boiling point of water liquid state and its vapor phase are in equilibrium, right? Gaseous state here. So these are at equilibrium. See, water composition is being same, no chemical reaction is changing, just chemical composition is remains same, but its physical states, here is liquid and here is in gas. So this kind of equilibriums are called physical equilibrium here. And chemical equilibrium means what? So chemical equilibrium means, yes, general chemical reactions are involved in that. Okay, So chemical reactions like formation of ammonia from like its reactants like N2 plus H2. This is an example of chemical equilibrium, you can say. Okay, right. So what I told you, the rates of forward and backward reactions are equal, then that state can be considered as equilibrium state. Okay, right. So for example, again I am writing A is in equilibrium with B, so that the rate of forward will be equals to rate of backward, I am saying now. So it means, how can you write a rate of forward reaction? See, rate of forward reaction will be, see, rate of forward means what? Moving from A to B now, this is what rate of forward. Okay, so the rate of forward reaction depends on concentration of this reactant molecule, that is directly proportional to the concentration of reactant molecule A. Similarly, what about rate of backward reaction? See, for a backward reaction, the reactant molecule will be now from here to here it is moving. So rate of backward reaction is proportional to the concentration of reactant, whatever the reactant we have here. Okay, so now I can remove this proportionality and replace with a constant Kf. Kf indicates what? Kf indicates equilibrium constant, I mean rate constant for forward reaction. Similarly, Rb I can write Kb concentration of B. Okay, like this we can write. So what we know, at equilibrium rate of backward and forward reactions are equal. It means Kf of A will be equals to Kb of B, right now? Now I am writing Kf by Kb. It means equilibrium like rate constant for forward by rate constant for backward will be equals to concentration of B by concentration of A. Okay, so this Kf, Kb, both of them are constants now. This is forward reaction constant, this is backward reaction constant. So this will be, both of them are constant, ratio of two constants will be again a constant. I am writing it as equilibrium constant Kc. Okay, so this is nothing but for a reversible reaction, the equilibrium constant at equilibrium we can write Kc is equals to concentration of product by concentration of reactant, that's it. This is a final conclusion, you can remember, very very important. Okay, now here the square bracket here I have represented, this indicates concentration, that is nothing but molarity. Okay, what is that? Molarity, mole per liters. Okay, what if sometimes in a chemical reaction in equilibrium gaseous molecules also involved right now, so that time you can take partial pressure of that particular gas, whether it is reactant or product, like gaseous products, if it is formed product B is a gas, then partial pressure of B by partial pressure of A or concentration of A, depending upon the data given you can fix your values over here. Hope it is also clear, right? Now if I want to express this, see, if I want to express this for solids, what happens to the solids? See, if any reactant or product is having like solid form, okay, then their concentration, or in perfect terminology we can say their activity for solids will be 1. Okay, I will show you one example so that you will get more clarity. See here I am writing CaCO3 forms CaO plus CO2. Okay, we know calcium carbonate is a solid substance here and calcium oxide is also solid, but this is a gas, right, its physical states. Now equilibrium constant if I want to write, what will be the general approach? Concentration of product by concentration of reactant. Whenever a solid substance is involved, whenever there is a solid substance involved, so its activity or its concentration is considered as unity, 1 you can say. So simply what is the other part we have? This one. So you just write concentration of CO2. If I want to write in terms of partial pressures, Kp will be equals to partial pressure of CO2, that's it. Okay, so Kc to express in terms of molar concentration, Kp to express in terms of partial pressure of reactants and products. Okay, right. Let me give you few more examples. See, I wanted to write it for N2 plus H2 gives rise to 2NH3 here. That's it. First balance the equation, right. Now in the exam they will ask one simple question. See, I will show you the PYQ so that you will get what we are going to discuss and what are the type of PYQs you are going to solve in next few minutes. See, let me show you the PYQ so that, see how basic it is. Once after knowing how to write equilibrium constant, you can able to solve this previous year question of EAPCET. The next this one also, okay, all these questions are very easy. See, all these questions you are going to solve now. See, multiple times repeated question it is. Very easy. Now within few minutes you are going to solve all these questions. Okay, right. Let me discuss this and let me give you clarity so that you can solve all this. Okay, see, if I want to write Kc, equilibrium constant, in terms of molar concentrations, you can write concentration of product, that is NH3. What is the stoichiometric coefficient we have? 2. Take it as a power of that particular substance. Here we are writing product NH3 with its with its coefficient 2, write it as 2 in the power. So again N2 to the power 1 and H2 to the power 3, just balance this 3, that's it. Okay, we got this for Kc. Similarly, if I ask for Kp, because this substance can exist in gaseous phase. Okay, so Kp means, how can you write? Partial pressure of NH3 square and partial pressure of H2 cube and partial pressure of N2, that's it. Okay, in the place of concentration I have just mentioned it as partial pressure. Now what will be the relation between Kp Kc? This is a question, the first question you can expect in the exam. Kp Kc relation, Kp and Kc relation, Kp Kc relation. So Kp Kc relation, how can you write? So Kp is equals to Kc RT power delta Ng. Okay, so how can you calculate this Kp and Kc? Simple. If the reaction involves gases, reactants or products, just calculate delta Ng. So delta Ng is very simple. Take the stoichiometric coefficients. What are the stoichiometric coefficient here for product? 2, and for reactant it is 3 and 1 right now. So you just take sum of stoichiometric coefficients of gaseous products minus sum of stoichiometric coefficients of gaseous reactants, that's it. Okay, so how many gaseous products are there here? 2, right? So you can take 2 minus how many gaseous reactants are there? 3 plus 1, 4. Okay, that's it. So delta Ng value is minus 2, that's it. So you can get Kp is equals to Kc RT power minus 2. So this is the relation for Kp Kc. In case of ammonia, formation of ammonia, this will be the relation. They will ask what is the relation for Kp Kc for the formation of ammonia or during the Haber's process for production of ammonia. They may ask like this, or they may ask whether Kp value is greater or Kc value is greater for production of ammonia. So how can you write this? Kp is equals to Kc by RT square, we can write now. It means Kp is smaller than this Kc because it is Kc by something right now. So you can say Kc is greater than Kp for this particular equation. Okay, hope this is very clear. Let me show you few questions on this. Look at this question, can you answer me this one? The equilibrium constant for the following given following reaction H2 plus I2 gives rise to 2Hi is correctly given by expression. Which expression shown is correct out of the 4 options? Very simple now. Writing Kc is easy here. Concentration of products, that is Hi to the power 2, and concentration of reactants I2, that's it. Okay, so where do we have this kind of option? Yes, fourth option we have, that will be your answer for the question. Next, look at this. In which case Kp and Kc are equal? Kp, Kc are equal. So just look here what to do. See, the given substance involve whether gaseous, reactants or products. So because what is the relation? Kp is equals to Kc RT power delta Ng. Right now, if delta Ng is 0, then this term becomes 0. Therefore, you can say Kp is equals to Kc. That's it. Right now, so identify Kp Kc relation will be equal in which case? If delta Ng is 0, then that case will be having Kp equals to Kc. So look at here, number of gaseous products are 2 and number of gaseous reactants are also 2. Therefore, delta Ng will be 0. Okay. So here also 1, 1, 2 minus this is 1, 1. This is you have 1 here. It means Kp not equals to Kc, but in first case Kp Kc are equal. Next, look at this case, 3 plus 1, 4 minus 2. This is 2 you have. It means Kp and Kc are not equal right now in this case also. And look at this, 2 minus 3. This is minus 1. It means Kp equals to Kc RT power minus 1. So this case also they are not equal. Only first option will be a perfect option for this particular question. Next, remember, whenever we are saying a reaction is at equilibrium, it means all its terms, like all its microscopic properties like concentration, macroscopic properties like concentration, density, color, pressure will remains constant. What I am saying, I am not saying they are exactly equal. They may equal or unequal, that depends on individual reaction, but I am saying they are constant. They are constant here. It means at equilibrium for a particular reaction having some color, that color remains same until that equilibrium is disturbed. Okay, if the reaction is moving forward, it might be fade out, or it might be intensity might be increased depending upon the reaction. Okay, right. So what to remember, all microscopic properties like pressure, volume, temperature, color, concentration, density will be remains constant. Okay. Now there are two types of equilibrium we are saying. One is static equilibrium and one more is dynamic equilibrium. See, our chemical reactions will be having dynamic equilibrium, not static here. Okay, in this discussion here. So dynamic equilibrium means what? See, for example, A to B formation is there now. Okay, so initially if you take only A, after some time B is formed. Okay, so when they attain this equilibrium point, after that point also some amount of A will converts into B form, and some amount of B is converts into A form. It means the total concentration of A and concentration of B remains the same throughout this dynamic equilibrium process. It means the amount which is converted from A to B will be equals to B to A after attaining this equilibrium. This is what the point you should remember. When it comes to static equilibrium, there is no movement of particles, like A cannot be moved to B, B cannot be moved for A once after attaining equilibrium. Okay, so I hope you got what exactly difference between dynamic equilibrium and static equilibrium. For simple, like you are seeing the escalator in the malls and everywhere. So if one step goes up, one step comes down, one step goes up, one step comes down. This is the thing you can understand in the case of dynamic equilibrium. Okay, right. Next, the state in which observable properties like pressure, temperature, volume and concentration will remains constant at this equilibrium point. Okay, you can remember this point. Okay, so now what, you might get one doubt now, sir, what if we change these terms? What if I change temperature? What happens to equilibrium? They will get disturbed. Okay, and if I change concentration, pressure, yes, if we change these values, their equilibrium get disturbed and they will try to attain a new equilibrium. Okay, yes, we need to study about that very clearly using Le-Chatelier principle. Okay, so once after solving the questions related to this basic thing, then we will move forward to the Le-Chatelier principle. Okay, once after understanding that, we will solve the questions on that also. Okay, right. Again, I hope you can easily answer this Kp-Kc relation is not equal. In which case? Just find delta Ng. If delta Ng is 0, then they are equal. If they are not equals to delta Ng not equals to 0, then Kp-Kc are not equal. That's it. Okay, you just try this and tell me in the chat box, and tell me what will be the expression for equilibrium constant for this reaction. Just now I told you concentration of product to the power its stoichiometric coefficient by concentration of reactant to the power their coefficients. Okay, it means Z cube, equilibrium constant Kc is equals to Z cube, concentration of Z cube by concentration of x square into concentration of y. That's it. So where do we have? Yes, option B will be your answer for the question. Okay, right. Look at this question. Can you answer me this? See, this is a new model question again. So before solving this question, you need to know little about this concept. See, I have a compound like Ha is a compound which is undergoing dissociation to give some compound like ions like H plus A minus. Okay, so now at initially I have only this Ha having 1 mole of this substance. Okay, therefore this is 0 0 initially at the beginning of this reaction. So after some time, what happens, since it is a weak electrolyte, dissociated to some extent and equilibrium is established. Okay, equilibrium generally seen in the case of weak electrolytes. Okay, next here what I am saying, out of this 1 mole of this substance A, some alpha is the degree of dissociation. It means the amount of Ha got dissociated will be indicated with symbol alpha here. Okay, so here also you can write alpha, because what are the amount dissociated here, those are forming this H plus and this A minus. Okay, hope this is clear right now. Now instead of saying 1 mole, sometimes we may use it to indicate with C mole. Then you can say this is C mole, this will be 0 0, and this I can write C minus C alpha, because its concentration is C having dissociation alpha, C minus C alpha. This is C alpha and this is also C alpha. These are the some ways to indicate. See, I am just writing here itself to avoid confusions, because sometimes you will be seeing like this and sometimes you will be seeing like this. So now what I can say, equilibrium constant Kc, how can I write concentration of products, that is H plus and A minus by Ha. Right now? Let me check, is there any blur in the screen? No, no. Yeah. Yeah. So now what are the values given here? See, what are the values we got here? For Ha ion, these are the concentration. For Ha minus ion, these are the concentration. For Ha, these are the concentration. You just write them here and you can substitute here for getting the final answers. Okay. Now based on these, so whenever there is blur, you just tell me, I will correct it on the screen. Okay. So just tell me what could be your answer for this question. Very simple. Look at this. The same way which we have did for the previous case, we can do it here also. See, N2 plus O2 combines to form this 2NO. Okay. What is the equilibrium constant Kc? given for this reaction. See, Kc means what we can write? Concentration of product NO to the power 2, concentration of N2 and concentration of O2 to the power 1 because they are having stoichiometric coefficients are 1. Okay, and the next, where the equilibrium concentration of N2, O2 and NO are found to be like this. It means initially they might be having some concentrations here, but at equilibrium these are the concentration. So equilibrium case only now we are calculating this equilibrium constant. Yes, just substitute these values over there, you will get your answer. So Kc is equals to NO. What is the value of NO? The last value, this is 3 into 10 power minus 3 square by N2. N2 is 4 into 10 power minus 3 and O2 3 into 10 power minus 3, that is it. Okay, so you can remove this 3 into 10 power minus 3 and this square as they are same, and this 10 power minus 3 and this 10 power minus 3. Finally, you have Kc as 3 by 4 right now. So you can say 0 point, so that it becomes 30 and 7s are 28, 4 7s are 28 and the next you are remaining with 2 and 0 5. So 0.75 will be your answer, that is first option will be the perfect answer for the question, right? Yeah, let's see some other questions related to this calculation of equilibrium concentrations or constants. Look at this. Which among the following relations denotes the correct relationship between Kp, Kc for the given reaction? See, multiple times asked, same model question or same question. See, how can you write Kp means? We discussed this. Kp can be given as partial pressure of B, partial pressure of C, okay, and partial pressure of A to the power 2. Similarly, Kc also you can write, but what we know Kp Kc relation? RT power delta Ng. See, they are saying everything is in gaseous state right now. So number of gaseous products are how many? 2. Gaseous reactants are also 2, like stoichiometric coefficients. Therefore, delta Ng becomes how much? 2 minus 2 means 0. If this term is 0, this whole term becomes how much? It will become 0. Okay, it will become 1. See, something power 0 will be 1, right? So this second term completely it becomes 1. Therefore, Kp will be equals to Kc. That's it. Okay, where do we have? Option 4. Okay, right. Next, look at this. Kp by Kc for the reaction at a T Kelvin is. Okay, so for the given reaction they are asking Kp by Kc relation. Okay, simple, again same question. See, all these questions are multiple times asked, very basic, very easy. You don't even need to spend your 1 minute time for this question right now. Let me set this. Okay, tell me. For this again, what they are asking? Kp by Kc. Kp by Kc. RT power delta Ng. Delta Ng is how much? Gaseous products are 1 minus, this is 1 plus 1 by 2, that is 3 by 2. Okay, this is 1 minus 3 by 2. So 2 minus 3 by 2 gives minus 1 by 2. So here minus 1 by 2 you got. Okay, so this is nothing but Kp by Kc is equals to 1 by RT power 1 by 2. Where do we have 1 by RT power 1 by 2? This is nothing but 1 by root RT only now. That's it. So option D will be your answer for the question. Very easy, right? Next, look at this. For ammonia formation from the constituent elements, expression for Kc is, we already did ammonia N2 plus 3H2 gives rise to 2NH3. Therefore, 2NH3 power 2 by H2 power cube power 3 and multiplied with N2. That's it. So here we have option B. See, we have a reaction for orthophosphoric acid like H3PO4 is given, final equation I am writing, which dissociates to give 3H plus and phosphate ion. So this is given as K4. Okay. So now they are asking what is the K4 value, equilibrium constant for this reaction, by looking at these first three reaction given, these first three equilibriums given, because H3PO4 can dissociate to give one H plus ion and form the remaining conjugate base, or it can release one more H plus ion from this conjugate base and form this one. Again from this HPO4 2 minus release one H plus ion to form this one. Okay. It is nothing but the reaction started with the starting material here and ended up with its phosphate, that is nothing but the ending material here right now. So simply just multiply these equations, just multiply these three reactions so that you will get that equation. See this one, this one, this one, this one. So finally what we have, H3PO4 plus 1H, 2H, 3H. So 3H plus and one remaining phosphate, that's it. So it means K4 is nothing but the multiplication of these three steps, K1 into K2 into K3, that's it. So where do we have this kind of equation? Right, option 4 will be your perfect answer for the question. Okay, and the same question might be asked with giving some values. For example, A gives rise to P, P gives rise to Q, Q gives to R, then what is the equilibrium constant for A to R, they will ask by mentioning this as K1 having some 10, K2 some 3, K4 K3 some value you can take anything like 2. Okay. So what about K4? Simply they will ask some giving some values here. I just mentioned this small numbers to make you feel clear and comfortable. Okay. So what to do? See, this P can be cancelled out. If I multiply this equation, this will be the scenario. If I multiply the given equations, the reactant of one reaction is product of the another reaction. Right now, see, reactant of this reaction is product of the first reaction. So cancel out LHS, RHS, same things are there, means we can cancel out, right? So simple. Therefore, K4 is nothing but K1 into K2 into K3. Okay. So that is 10 into 3 into 2, that is 60 here. Okay, that's it. This is how you can simply answer the basic questions, right? If you look at these two questions, what they are saying, see, the equilibrium constant for a reaction is mentioned. The reaction I am writing here, A plus Z B ZB or BB. Okay, this is a reaction they have mentioned, equilibrium reaction they have mentioned. Okay, if the reaction takes place in the following form, so what they are saying, if the same reaction takes place in this following form, okay, for this case is the equilibrium constant. So for this reaction, what is the equilibrium constant Kc dash? How can you relate them? See, simple now, what they did, they have multiplied this first equilibrium reaction with a number 2 here right now. When a equilibrium reaction is multiplied with some number, you take its new equilibrium constant as the power of this old equilibrium. Okay, it means whatever that number they have multiplied, you just take it as a power to that old equilibrium to get the new equilibrium constant value. So Kc dash is equals to Kc power 2. Okay, if I multiply this equation with n, then Kc power n, that's it. Okay, so I hope it is clear for this reaction. So Kc dash will be equals to Kc power 2, that is first option. And then next, if the same reaction divided by 2, see, if the reaction is divided by 2 is nothing but they are multiplying with 1 by 2 only now, that's it. So our new Kc dash will be equals to Kc power 1 by 2. If they are dividing the equation with some number n, then you take 1 by n, that's it. Okay, hope the concept is clear. Right, let's see this question. You can easily answer this. See, if the reaction like A to B is given as Kc, its equilibrium constant is given as Kc, then Kc, which is value equals to 3, I am saying. Then what if B is giving rise to A, what is its equilibrium constant? What happens to this equilibrium constant? What is the value? See, Kc means what? You can write equilibrium constant for first reaction. Kc is equals to B by concentration of A. Right now, for this reaction, how can you write? Kc dash equals to A by concentration of B. So how do they relate it? So just what I did, I just reversed the reaction. So when we reverse the reaction, its Kc dash becomes inverted. It means what? Kc dash is equals to 1 by Kc. When a reaction is reversed, its equilibrium constant becomes inversed. Okay, see, it is inversed here. It is A, B by A, here A by B. Okay, now read this question. You can easily answer this by understanding this two-step question, two-step concept. See, this is the reaction given at a temperature T Kelvin, Kc for the given value. Let me check whether it is visible or not. No. Tell me. This is the reaction given Kc as 50. The Kc value for a new equation which is given in this way at the same temperature will be. Okay. So what makes the difference from here to here? Equation 1 and equation 2, if you see, how do they differ 1 and 2? It's very simple. Equation 1 is reversed and multiplied with number 3. Okay. So if it is multiplied with 3, it becomes multiply with 3. So 3 cancel, it becomes N2 plus here it becomes 3H2, and this 3 here, if I will get 2 NH3. Yes. So if I multiply this equation, we will get this one. But here it is reverse of this. It means our Kc dash, a new Kc dash for this reaction, Kc dash will be equals to, reaction is inverse, it means 1 by Kc and multiplied with number 3 now. So you just take power 3, that's it. So 1 by Kc cube is our Kc dash. Okay. So the value here given is 1 by 50 is given now, 50 cube you take. Okay. So 50 cube means you can write it as 1 by 125 125 into 10 power 3, I am writing here 10 power minus 3. Okay, 1 by 125, nowhere we have option here. Here simply I can write this as multiplied with 3, that is 1000, and divided with 3, that is 10 power minus 3. Okay. So next, so when it comes this 125 means how many times? See, 25 5s are 25 4 0. So this is 8 times right now. So 8 into 10 power minus 6 will be your answer for the question. So Kc dash is how much? 8 into 10 power minus 6. So option B will be your answer for the question. How easy these questions are right now? Very simple. Okay, practice few more questions once after this session is completed, or look back into these questions on your own so that you will get more confidence to solve the questions even when you attempt some exams. Okay, right. Look at this question. Look at this question. Consider the following reaction in a 1 liter vessel, closed vessel. If all the species N2, H2, NH3 are in 1 mole in the beginning and equilibrium is attained after unreacted N2 is 0.7 mole. What is the value of equilibrium constant? See, very simple reaction it is and simple answer it is N2 plus 3H2 gives rise to 2NH3, right now. What is the mole ratio we have? 1, 3, 2, okay. That is what its equilibrium stoichiometric coefficients, right now. So now what they are saying, if all species, all the reactants and products are in 1 mole in the beginning, it means at the starting of the reaction they have 1 mole reactants and 1 mole product also, okay. Hope this is clear. Next, see at the equilibrium, when this is at the starting, at the beginning, so at beginning, at the equilibrium case, they are saying the ammonia remained unreacted is how much? 0.7 remained unreacted. It means we know from these, as time goes on, some of this reactant will converts into product now, that is 1 minus x here, and this is 1 minus 3x. Why I am writing 3x? See, because stoichiometric coefficient here is 3, that is why 3x, and here it is 1, that is why 1 minus 1x, okay. And here 1 minus 1, this is forming product now, so some quantity of product is increased. So how much it is? 1 plus stoichiometric coefficient is 2x, that is it, okay, right. So now this 1 minus x value is how much they are saying? 0.7, 1 minus x is 0.7. Then x value, how much amount it is consumed? 0.7 means 1 minus 0.7, that is 0.3, that is it, okay. So here it is 0.7, this is 1 minus 3 into 0.3, that is 0.9, you can have 0.1, and this will be 1 plus 2 into 0.3, 0.6 and 1.6 is the amount of product formed, that is it. Up to here it is clear, right. So now what is the value of equilibrium constant? That is Kc is nothing but ammonia concentration to the power its stoichiometric coefficient, N2 to the power its stoichiometric coefficient, H2 concentration to the power its stoichiometric coefficient. Here it is 1.6 square and here N2 is 0.7 and H2 is 0.1 to the power 3, right. Next, these you can write 16 square is 256 right now. So you can write 2.56 as decimal is there here, and this will be 10 power minus 3, right now this is 10 power minus 3, it means you can write it as 10 power plus 3 here, 1000 I can write, okay. And what about this? This is 0.7, 0.7 means I can remove this 25.6 by 7 I can write. So 7 ones are, and this is 3 is 21, and we have 4.6, so you can write 46 by placing a decimal after 3, okay. So next 6 are 42, 42 means again we still have 4, means I can write 5 times 35, 7 5 is 35, okay. Again we have 5 around, okay, we have 7 around, so it means 49, okay. So see here, just multiply this number so that you will get 3657, yes, like this. So we have this option B as our answer for this question, okay, right. Hope everything that we are discussing here are clear without any confusions. Yeah. Can you answer me this? Can you answer me this for the same model, same concept is involved here? See, the given reaction is mentioned in this way, having equilibrium constant as K. Then this reaction is turned into this format, then what will be its equilibrium constant, that new equilibrium constant, Kc dash is how much, okay. So if you know this answer, just mention in the chat box, I am looking into it, yes. Yeah, so what happened here? The reaction is divided by 2, therefore its equilibrium constant will become k to the power 1 by 2. If it is divided by 2, it will become 1 by 2, that is it. So, here we have fourth option. Okay, right. Next, can you answer me this? Anyone in the chat box or those who are watching this video can answer in the chat box. Even it is wrong, no issues, will help in the chat box if you answer. Whether it is correct or not, it's a secondary thing. Okay, just answer me this in the chat box. So, what is the use and what is the application of this equilibrium constant? See, Kc value for a reversible reaction, Kc value lies from 10 to the power 3 to 10 to the power minus 3. What I am saying, 10 to the power 3 to 10 to the power minus 3. So, in this range we can say reversible reactions are exist. Okay. So, if Kc value is very greater, so it means Kc value is very higher, then we can say reaction is favoring forward. Okay. And if Kc value is very small, that means reaction is favoring backward. See, why Kc value higher means forward? Because we are writing Kc equals to concentration of product by concentration of reactant. No? If this product value is greater, the Kc value also be greater. No? That is what. If higher Kc value, greater is the forward direction. Okay? Greater is the forward direction for the given reaction. Okay? Right. So, this is again little important discussion. These points are very important here. Next, how can we predict which direction the reaction is moving? See, I have a reaction like equilibrium reaction A to B. Okay, if this reaction is at equilibrium, I can call it as equilibrium constant Kc. And sometimes what happens, due to some disturbance or due to some factors, this reaction might be favored forward. Right now, if it is favored more towards forward, we should indicate that this equilibrium moving forward in this manner. Okay, and this is not anymore an equilibrium state. This is reaction is moving towards forward now. So, here whatever the ratios of their concentrations you are writing, like concentration of B by concentration of A we are writing now. If we are writing this at equilibrium, we are saying it as Kc, but other than Kc, it means other than equilibrium condition, if we write the ratios of product by concentration of reactant, you should not call it as Kc, you should say it as Qc, that is reaction quotient. So, what is mean by reaction quotient? Reaction quotient is a concentration of product by concentration of reactant at any other condition other than this equilibrium states, at any other state other than this equilibrium state I am saying. Okay. So, it can be also favors for backward, like you should indicate the arrow mark more moving towards A side and smaller towards B side. Okay. So, it means here equilibrium is favoring towards back side. Okay. So, now Qc here. Okay. So, now here just understand this thing. What is the thing you can write here? Concentration of B by concentration of A we will be writing right now. But we know reaction is more favoring more towards A side, means the value of A will be more here. It means Qc will be less than Kc here. Right now at this condition Qc will be less than Kc. It means when Qc is less than Kc, again remember, whenever a reaction is favoring backwards forward we are saying now. So, due to some disturbance it might be happening like that, but for any reaction which is having reversibility will always tends to occupy attain this equilibrium states, always, whether it is moving backward or forward, always if we adjust the again conditions properly, again it will tends back to its equilibrium state. So, if Kc is less than Qc is less than Kc, now in order to attain that Kc, it means both should equal like this now, it means reaction should move forward. If reaction is moving forward, then value of A and value of B becomes almost same, that is ratio becomes same, and Qc and Kc will be almost equals to this Kc. Okay, in order to become Kc, reaction should move forward, then only Qc will become Kc. So what I can say, if Qc is less than Kc, reaction favors forward. Okay, this is a simple statement you can remember. And in this case, Kc is less than Qc because concentration of product is more here, it is moving more towards product side. So in this case, in order to attain equilibrium, reaction moves backward. Okay, so when Qc is greater than Kc, reaction moves backward. If Qc is less than Kc, reaction moves forward. Okay, why they are moving? Because any system in this nature always try to attain equilibrium, because equilibrium is the most stable state with the maximum randomness, you can remember. Okay, maximum randomness and minimum Gibbs free energy will be observed or will be attained at this equilibrium state. Okay, remember this point, very important. What I am saying, maximum randomness and minimum Gibbs free energy will be observed at the equilibrium state. Okay, remember. Okay, so due to that factor, always the reactions, I mean this reversible reaction tries to attain equilibrium conditions. Okay, and these conditions are very important. If Qc is smaller, then equilibrium tends to move forward to attain Qc equals to Kc, that is equilibrium. Okay, and if Qc is greater than Kc, then reaction favors backward to attain equilibrium, therefore Qc becomes equals to Kc. Okay, right. This dissociation we already discussed. About this Le-Chatelier principle, yes, Le-Chatelier principle and its application will be discussed in the next session. So you just follow the channel and click on the like button if you like the content, and you can share with your friends, those who are preparing for EAPCET, NEET, JEE. Okay, and that's it. If you have any queries or concerns, you just mention in the comment box. We will be looking into it and you can happily learn these concepts. Okay, so thanks for watching. Stay connected.